Okay friends, I am now showing you 10 examples. Let us see what type of function has been given, what is the region of integration, are there any special difficulties. This is what we will have to look for. My first example is a function in the Cartesian frame 1 minus 6x square y, and from the limits we can make out that the region is rectangular. In fact, it's a square. So the problem is to evaluate this integral. So this region is rectangular. So you can straight away use them as the limits of integration. Integral 0 to 2, integral minus 1 to plus 1, 1 minus 6x square y dy dx. This integration is straightforward. 0 to 2 y minus 6 x square y square by 2. So 3 x squared y squared from minus 1 to 1. So let's integrate this one with respect to y. In fact, with respect to x. 0 to 2 1 minus 3x squared minus of minus 1 minus 3x square dx. So these two would go and we are left with integral 0 to 2 1 plus 1 2 dx. So we get 2x from 0 to 2, and you'll have 2 into 2 4, and the correct option for this problem is C. So this is a problem without any complication, right? Straightforward integration that became possible because the region was rectangle. Okay, now let us go to the second question. The second question is integral 0 to 2 integral 1 to e power x dy dx. So here the function is f of x y is equal to 1. That means we are actually evaluating area. Now, is there any difficulty about this integration? The answer is no. This is straightforward. 0 to 2 from 1 to e power x dx. So 0 to 2 e power x minus 1. So this is plain integration, and we'll have e power x minus x from 0 to 2. Okay, so we'll get e square minus 2 minus of 1 minus 0. So you will have e square minus 3 as the result, and the correct option is A. So again, there is no complication about this integration. So let's take the next question. The problem is integral 0 to 3 integral 1 to square root of 4 minus y x plus y dx dy. It's a plain evaluation problem, but the difficulty many students face is, the basics of integration itself. So the first observation is the order dy dx given is not correct. So you'll have to first make it dx dy because you've got functions of y in the inner integral. So we must first change that to x plus y dx dy. So let's prepare the integration for this. 0 to 3 x square by 2 plus xy from 1 to square root of 4 minus y dy. Be cautious because the lower limit also contributes. So we'll have 4 minus y by 2 plus y root square root of 4 minus y minus half minus y dy. This will be 4 by 2, 2. 2 minus 1 is 3 by 2. Minus y by 2 minus y is minus 3 by 2y plus y root square root of 4 minus y dy. So you can find that there is nothing much to be worried about these two, but the integration of this with respect to y is going to be important. So first what I do is, I will just call this 1. I'll concentrate on this integration and then I will feed it into this one. So integral y root 4 minus y dy from 0 to 3. Several methods are there, but the easiest would be 4 minus y is equal to t squared. So y is equal to 4 minus t squared. Dy is minus 2t dt. Of course, limits will change. Y is equal to 0 implies t square is 4, so t is 2. We'll take the positive sign. Y is equal to 3 implies t square is equal to 1. We'll take t is equal to 1. So these are the details of substitution. So we can have 2 to 1, but there is a minus sign in the derivative. So we'll interchange that and convert it as integral 1 to 2. Now y is 4 minus t square. This is now square root of t square, that is t, and then 2t dt. Right? So what is that we have to integrate? 2t square into 4, 8t squared minus 2t to the power of 4. So this is 8t cube by 3 minus 2t to the power of 5 by 5 from 1 to 2. Right? So how much will this come to? 8 into 8, 64 by 3 minus 32 into 2, 64 by 5 minus of 8 by 3 minus 2 by 5. So you can evaluate that. That's not a big problem. So now we have this integration to complete. 3y by 2 minus 3y square by 4 plus whatever is the answer you are getting from there. Of course, we'll have to do one important thing. This integral is already being evaluated from 0 to 3. So therefore, we'll put the limit 0 to 3 for the first pair, and then whatever is the answer you are picking up from there. So you please work it out, and you will get 241 by 60 as a final output, corresponding to option B. So I'm just leaving that small simplification to the student, and then don't forget to attach it to this part. And double integral of square root of x square plus y square dx dy, and the region is specified like this. So this corresponds to the region of integration. So all of us can easily understand this region. It is the interior of a circular disc. So this circle is x square plus y square is equal to a square. So when we say less than or equal to, it is the interior of this circular disc. Now this is an ideal problem where we can convert into plane polar coordinates. Alright. So using the transformations, x is equal to r cos theta, y is equal to r sin theta, with a Jacobian r, which means dx dy gets transformed into r dr d theta, which means the limits for r and theta will have to be determined. That is because the given integral is now getting converted into a polar double integral. the function becomes square root of r square because x square plus y squared here will give you r square into r dr d theta. Now please observe that r varies from 0 to the radius of this circle because the region grows from a point to a circle of radius a. So r limits will be 0 to a, and because the radius vector covers 360 degrees to generate this region, theta varies from 0 to 2 pi. So theta limits will be 0 to 2 pi, r limits will be 0 to a. So please observe the integration has become very simple because this is r square. So when you integrate, you will get r cube by 3 from 0 to a d theta. So this becomes a cube by 3 into the integration of d theta is theta. Therefore, you will get 2 pi by 3 a cube as the answer. And you will find that the correct option for this problem is D. So what I want to explain through this problem is that we must recognize the problem is set with respect to the polar coordinate system. And how do we recognize? First, the region circular, and another very important signature in this problem is x square plus y square in the function. Whenever you have x square plus y square in the function and a polar curve like a circle, it is a perfect case for using the polar coordinate system. So this is something that many students will have to practice because the problem may look very tough externally, but if you know the concepts, it just takes a couple of minutes. Let's go to the next problem. Is double integral x squared plus y squared dx dy over r, and r is bounded by three curves y is equal to x squared, x is equal to 2 and y is equal to 1. Now you can see that there is a parabola and two straight lines. So the region is not rectangular or square. So let's draw a simple diagram. This is y is equal to x squared. This is the line x is equal to 2. So this intersection point will be 2, 4. For x is equal to 2, y is equal to 4. Then we have y is equal to 1. Remember, this height is 4 units. So y is equal to 1 will be a straight line like that below that point of intersection. So this is y is equal to 1. So the region of integration is that. So this is the curve y is equal to x squared. This is the line x is equal to 2. This is the line y is equal to 1. So this intersection point will be x is equal to 2 comma y is equal to 1. This intersection point is when y is equal to 1, x is equal to 1. So the corner points of this region are 1 comma 1, 2 comma 1, 2 comma 4, and this is not a triangle because this curve is parabolic. Alright, now that can be visualized as an Rx region or an Ry region. Both are possible. Suppose you take Rs and Rx region. Then the x limits will be x is equal to 1 to x is equal to 2. This is the lower curve, so y is equal to 1 is the lower limit, and this is the upper curve, y is equal to x square. So when you apply the limits, you will get integral 1 to 2, integral 1 to x square plus y squared dy dx. This integration is straightforward, and we will get the answer to be the option D. The next question is again based on conversion to polar coordinates. The problem is to evaluate square root of x square plus y square dx dy and R enclosed by x squared plus y squared is equal to 4 and x squared plus y squared is equal to 9. So you can see that we have a smaller circle of radius 4 and a bigger circle of radius 9. So the region is that. So we can call this an annulus. Now please recognize that once the region is bounded by polar curves like circle, and we have got an added advantage that we have x square plus y square in the function. So transform into plane polar coordinates. I mean x is r cos theta, y is r sin theta, Jacobian is r, dx dy is r dr d theta. R varies from is not 4 but 2 because radius is 2 and this is 3. So R varies from 2 to 3. What about theta? Theta varies from 0 to 2 pi because all the quadrants are covered. So R varies from 2 to 3 and then theta varies from 0 to 2 pi. So let us evaluate now. I is equal to 0 to 2 pi, 2 to 3, square root of r square, r dr d theta. This is simple. This is r square, r cube by 3, 2 to 3 d theta. So this will be 1 by 3, 0 to 2 pi, 27 minus 8, that is 19 d theta. So you will get 19 into 2 pi, 38 pi by 3. So you will find the correct option is A. So this is the second example we are doing using polar coordinates. The first one was a plane circle. This time it is an annulus. So polar coordinates can be very, very useful for these types of problems. Let's go to the next question. Integral 1 to log 8, 0 to log y, e power x plus y. So the correct order should be dx dy. Okay. The first integration with respect to x. So first what we do is we split this as e power x into e power y dx dy. First integration with respect to x. So we'll have 1 to log 8. Integration of e power x is e power x itself from 0 to log y into e power y dy. So when you apply limits, e power log y becomes y minus e power 0 becomes 1 into e power y dy. This you can integrate by parts. So when you integrate by parts, you get y minus 1 into e to the power of y minus 1 into e to the power of y from 1 to log 8. So if you simplify this, you will get y minus 2 into e power y from 1 to log 8. So you will get log 8 minus 2 into e power log 8 is 8 minus 1 minus 2 is minus 1 into e power 1 is e. So you will get 8 log 8 plus e minus 16. So this is the answer to the problem, and the correct option is B. So there is no major challenge in this problem. This problem has been selected just to handle logarithms and exponential functions. Let us go to the next question. This problem has been selected to look at the changing order of integration technique. So the problem is, after changing the order of integration integral 0 to 3 integral 1 to square root of 4 minus y x plus y dx dy appears as what? In order to do this problem, we must look at the limits and recognize whether the region is an Rx region or an Ry region. If it is Rx, change it as Ry. If it is Ry, change it as Rx. So, you know these are x limits, these are y limits. So, y is equal to 0 to 3, x is equal to 1 to square root of 4 minus y. So, the region is Ry region. How to understand? If you look at this one, this is nothing but x is equal to square root of 4 minus y. So, x square is equal to minus of y minus 4. So, that is a vertical parabola having vertex above and mouth downwards. So, this is the parabola, vertex at 0, 4. Let us look at the other limits. Y is equal to 0 is the x-axis, y is equal to 3 is a line parallel to x-axis, but observe it is below the vertex because the vertex is at 0, 4. Then this point of intersection has to be found. This equation is x is equal to square root of 4 minus y. So when y is equal to 3 substituted here, you will get x is equal to 1. Therefore, this point is 1, 3. This is 0, 4, this is 1, 3. So, x is equal to 1 should be that line. Now, let us see what is the region. The region is between y is equal to 0 to y is equal to 3, between x is equal to 1 and x is equal to parabola. So, this is the region of integration. That is the region of integration. And we have already recognized this is an Ry region. So, what is that we need to do? We need to transform that region into an Rx region. So, just go to the region. So, this region is just that itself, but let us write the details. This is 1, 0. This is when y is equal to 0, you will get x is equal to 2, 0, and this point is already identified as 1, 3. So, I want to see this region as an Rx region. Because that was Ry, I should see this as Rx. So, for this Rx region, let us first write x limits. X is equal to 1 to x is equal to 2. This is the lower limit of y is equal to 0. This is the upper limit of y. The upper limit of y will come from this equation. So y is equal to 4 minus x squared. Y is equal to 0 to y is equal to 4 minus x squared. Therefore, the new integral is integral 1 to 2, integral 0 to 4 minus x squared, x plus y dy dx. So please observe, the limits have undergone major changes. This is with respect to an ry region and this is with respect to an rx region. That is a question. The question was, after changing the order of integration, how does this integral appear? It appears like this. And the correct option for this problem is option A. The next problem is again based on changing order of integration. The problem is integral 0 to pi, integral x to pi, sin y by y dy dx. Please observe that the first integration with respect to y cannot be initiated because sin y by y cannot be integrated. So we change the order of integration. So this is an Rx region because these are y limits, these must be x limits. X is equal to 0 to x is equal to pi, y is equal to x to y is equal to pi. So when you draw this region, x is equal to 0 is y axis, x is equal to pi is a line parallel to y axis. Then we have y is equal to x and this point happens to be pi comma pi, so that y is equal to pi passes through that point. So the region is between x is equal to 0 to x is equal to pi, between y is equal to x to y is equal to pi. So that is the region of integration. So when you see this in Ry, y varies from 0 to pi, x varies from x is equal to 0 to x is equal to y. So this integral will change and will have 0 to pi. I am writing these limits, 0 to y, sin y by y. The changed order is dx dy. Now this integration is possible because with respect to x, this is a constant. So we will have 0 to pi sin y by y into x from 0 to y dy. So when this becomes y, these two will get cancelled and we will have integral 0 to pi sin y dy. The integration of sin y is minus cos y from 0 to pi. So what is that we get? Minus of cos pi is minus 1, cos 0 is 1 and you will get 2. So what was not possible at all in Rx became possible because we converted into an Ry region. So therefore, changing order of integration can be a potential area where the student can be tested in major competitive exams. So the answer to this problem, as you can observe, is option D. The problem is, what will be the value of this double integral where the region is x greater than or equal to 0, y greater than or equal to 0, and x squared plus y squared less than or equal to 100. Now there are two ways of doing this problem. One is by actual integration, one is by very good observational power. I'll explain both the things. Now please observe, this means you are confining to the first quadrant of the xy plane, and this is a circle of radius 10. So we want to look at a circle of radius 10 in the first quadrant. So this is the region of integration. Origin to 10, 0, 0, 10. So it's a quadrant of a circle of radius 10 units. Now method 1, this is already in polar. Theta varies from 0 to pi by 2 because we are in the first quadrant. Then 0 to 10 r dr dt. So 0 to pi by 2 r square by 2, 0 to 10 d theta. So this is 100 by 2, 50. So 0 to pi by 2, 50 d theta. So this becomes 50 theta, where theta is pi by 2. So we'll get 25 pi. So this is if you are not approaching through any concept, you are just looking at the situation and then fixing the limits. Then what is method 2? Method 2 is nothing but double integral r dr d theta is identically equal to double integral 1 dx dy. Right? Because in an earlier example we saw this like this. Now we are seeing this in the reverse direction. But we all know this is nothing but area of R. Area of R means area of this region. So it is nothing but 1/4 pi r square, where r is equal to 10. So 1/4 into pi into 10 squared. So that's the same as 25 pi. So whether you innocently proceed or proceed intelligently, you will get the same result. So 25 pi is the correct answer, and the correct option for this problem is C. So these are some of the examples I have decided to explain in this lecture, and we advise students to look into standard textbooks and then collect problems where you get good command over changing order of integration, changing the polar coordinates, and changing the variables using transformations. Let us not forget the importance of the Jacobian in the process.